Imagine needing an engineer with specialized equipment spending an hour to set up your phone's camera before you could take a photo. Absurd, right? Yet that's exactly how augmented and virtual reality devices worked just years ago. Today, computer vision has transformed a complex technical barrier into something so seamless you never notice it happening. This is the story of how camera calibration went from lab procedure to invisible magic. Traditional camera calibration demanded precision-printed checkerboard patterns, controlled lighting environments, and technicians trained in optical systems. Each device required 30 to 60 minutes of manual setup. Move the camera slightly, recalibrate. Temperature change, recalibrate again. This process created a massive bottleneck. AR/VR technology couldn't scale to consumers when every headset needed a computer vision specialist to make it work properly. Camera calibration determines how accurately devices understand spatial relationships in the world. Poor calibration means misaligned virtual objects, drifting holograms, and nauseating VR experiences. For professional applications like surgical AR or autonomous vehicles, calibration errors could mean life-or-death mistakes. It's the invisible foundation that determines whether augmented reality feels magical or broken. Without proper calibration, no computer vision system can function reliably. Modern computer vision uses structure from motion algorithms that calibrate cameras automatically during normal operation. By analyzing how visual features move across frames, these systems calculate precise camera parameters without checkerboards or technicians. The calibration happens in real time, continuously correcting for drift and environmental changes. What once required controlled conditions now works invisibly in your pocket, on the street, or in your living room. Face filters and AR effects on smartphones seem simple, but they require precise camera calibration to track faces and anchor virtual objects. Computer vision enables millions of phones to self-calibrate instantly when you open the camera app. No setup screens, no calibration wizards, just point and shoot. This 95% reduction in setup time transformed AR from specialist tool to mass-market entertainment, enabling a multi-billion-dollar ecosystem. Modern VR headsets like Quest or Vision Pro self-calibrate their multiple cameras within seconds of powering on. Inside-out tracking systems continuously refine calibration as you move through space, correcting drift automatically. This invisible process eliminated the need for external sensors and technical setup that plagued early VR. The result? Consumer adoption skyrocketed when the technology became truly plug-and-play accessible. In manufacturing and warehousing, thousands of robot-mounted cameras now self-calibrate without stopping production lines. Computer vision systems detect and correct calibration drift caused by vibration, temperature fluctuations, and mechanical wear. What once required shutdown and specialist technicians now happens autonomously. This enables 24/7 operation and dramatically reduces maintenance costs, making automated visual inspection economically viable for mid-sized manufacturers. Self-calibration relies on simultaneous localization and mapping, bundle adjustment algorithms, and increasingly, deep learning models that predict calibration parameters from raw image data. These systems process sensor fusion from IMUs, depth sensors, and multiple cameras. Edge computing enables real-time processing without cloud connectivity. The convergence of these technologies made consumer-grade self-calibration possible, running efficiently on smartphone processors. Emerging research focuses on neural networks that eliminate explicit calibration entirely, learning to compensate for camera distortions implicitly during scene understanding. Generative models may soon synthesize perfect calibration from uncalibrated imagery. As computational photography advances, the distinction between calibrated and uncalibrated cameras may disappear completely. The next generation won't just self-calibrate, they'll render the entire concept obsolete. Self-calibrating systems represent just one example of how computer vision is reshaping human-computer interaction. From invisible infrastructure to breakthrough applications, this field defines the next decade of technology. Whether you're building AR experiences, developing robotics, or simply curious about the tech you use daily, understanding these systems unlocks new possibilities. Check out my book, Computer Vision in AR and VR, link in the description. Start your journey today.